Hello girls, remember I had given you a short note on the laws of inheritance shown by Mendel. That note I gave you so that if it comes for short marks, for short notes or with less marks, then you can write this shortened one. Okay, this is a very short and a very easy one. It's very easy, but better that we see the laws in detail. Okay. Okay. So last time I had given you about the history of the monk Gregor Mendel, no? So the Mendelian concept of hereditary, they were derived by Gregor Mendel, a 19th century monk who conducted the hybridization experiments of garden pea between 1856 and 1863. Okay, he cultivated and tested around 28,000 something. Roughly, they are giving 29,000 pea plants. And from those experiments, he concluded or he deduced two general assumptions, two ideas, okay, which later we know them as Mendel's law of hereditary or Mendelian inheritance. Okay, now that one he has to prove his theory, right? Like for example, Einstein proved the theory E is equal to mc square. Now how, right? How will I know that it was done by Einstein? How do I know that this law exists? He has to publish it in a paper, okay? Like a paper or a journal. The same way you have your Vogue magazines, where you see on the cover, right, Gigi Hadid, suppose, she is showing a new dress by, let's say, Tommy Hilfiger. How do you know? Because they published it in that magazine, no, that this is a new dress that has been created by this designer. So same here, okay? This experiment has been done and conducted by this scientist and he is publishing it in this scientific journal. You get it? Just like E is equal to mc squared was published in some scientific journal, then even here, so he has published in some papers, okay? And the name of the paper is Experiment on Plant Hybridization, and that he read to the Natural History Society, and it was published in 1866. Okay, so this is just his history, so really required. But I just felt that you have to know about the father of genetics. So from his findings, other scientists, they started to be able to express or to predict the expression of traits on mathematical probability. Okay, so remember that Punnett square we draw, like the 9 is to 3 is to 3 is to 1 ratio. That is nothing but probability, right? He is saying probably out of 16 crops, 9 will be tall, 1 will be dwarf, 3 will be hybrid, and another 3 will be hybrid. So it's a probability. Okay, so everything is based on probability. See, for example, the probability of if I toss a coin in the air, probability it will come head or tail is 50%. No, because it has two sides. So either head will come or either tail will come. So same here. So from this statistics, from this probability, other scientists could deduce, okay, could understand about hereditary even more. So the contribution of his success can be because of true breeding. Okay, he was very specific. He was very neat and tidy. Okay, when he what he did is, suppose he wants to crossbreed, okay, between a tall and a dwarf with forceps and gloves. Maybe he wore gloves, no? Forceps and gloves, and in a very a good place where there's no wind, he cut with scissors the male part of the tall plant, okay, and then one androgyme from the dwarf plant, he just dusted it. Okay, oh, somebody messaged me. He just dust the pollen from the dwarf. Okay, so he did very much controlled experiment. Okay, he is, because he's such a scientific man, no, such a scientific person, that he has done true breeding. Means he didn't allow it to nature, no, he didn't allow the wind, the air, the insects to carry. He did by himself. Okay, true breeding. So he chose these crops that he knew that they are, this one is tall and this one is dwarf. He was sure, 100% sure. Okay, and it's not like this is a mix or a hybrid plant, a new plant, nothing like that. So he started his crosses with the plants that were true breeding, and he measured only binary characteristics. Okay, means that were absolute. Okay, like a Chinese person will give birth to a Chinese child. No, it's not possible that the Chinese person will give birth to English child. No, it will not look British. Okay, so he measured only the absolute characters, those characters which can be seen. He did not measure like genetic how do I say, like he measured something that he is sure. Okay, either the height or the color or the shape of the seed. Okay, these sure short characteristics only he measured. Okay, so he measured only absolute characteristics such as color, shape and position of the offspring, rather than the quantitative characteristic. Remember, we had done last year about qualitative and quantitative. Quantitative, you have to count, no? Like he didn't have to count the genes. Okay, he went only for the quality, like for the color, for the shape, for the length. You know, he didn't go for the quantitative, like how many exact yellow. Like there has to be fully only 24 or fully only 24.5. He didn't go for the number, he went for the quality only. So his method of data analysis and his large sample size gave credibility to this data. Okay, means gave it a full marks. And he also had the foresight. Okay, means when foresight, we see, he could see far. Okay, that if I do only one generation, is no point. I have to do many generations of crossing, then only I can be sure. Okay, so he's a true scientist. He knows that he has to keep on repeating it so many times until he's absolutely sure. Then he also performed test crosses or back crossing. Okay, so you will learn with with another miss about test crossing. Okay, like after he's crossed them, he performed test cross back with the parent to see if what he predict will come true. And obviously it came true. No, like he thought, find one of these 9:1, the one generation is a dwarf. Now if I cross this dwarf with one parent, I should get this. And when he crossed like that, he really got what he predicted. So he had this foresight to perform the back crosses. Okay, so now let's look at his laws.